The Voyager 2 spacecraft is one of the great testaments of human ingenuity. More than 4 decades after launch, the spacecraft continues to function, even in the harshest imaginable condition of deep space. Despite being billions of miles away, the tenacious spacecraft continues to send back amazing and even terrifying discoveries to the mission controllers on Earth. One of the discoveries was a huge wall of fire when Voyager 2 crossed the boundary of our solar system. What happens at this boundary, and how do the events at this boundary affect us on Earth? What has made the Voyager 2 spacecraft last as long as it has and still be able to remain in communication with the Earth? Well, while the arrays of sensors and transmitters are important, they are nothing without the power source. In fact, they would have stopped sending back signals many years ago if the power source had run out. The Voyager 1 and 2 spacecraft are not powered by solar. That wouldn't work when they are so far from the Sun. Instead, they use radioisotope thermoelectric generators, or RTG, for their energy. Each of the Voyager probes has 3 RTGs, and they use plutonium-238 for their fuel source. As the isotope decays, it produces heat, which is converted to electrical energy. When the Voyagers initially launched, they were generating 470 watts at 30 volts DC, but over time that has reduced. But it's not just the fuel declining, as the thermocouples used in the system also degraded over time. As of 2011, the Voyagers were generating just under 270 watts each, about 76% of the power at the beginning of the mission. However, the spacecraft has an additional source of power on board, which is also critical to its operation. They have small thrusters that allow them to be reoriented to face the Earth for communication when necessary. These thrusters have a tank of hydrazine fuel that they draw from, and even though they only work in bursts, they will eventually run out. One interesting detail about the thrusters is that they have a backup. After 37 years, the main thrusters were no longer working efficiently, so NASA switched to the backup thrusters, which had not functioned for almost 40 years, and they worked perfectly. Deep in the darkness of space, where even sunlight cannot reach, Voyager 2 has marked a massive milestone in space exploration. It has become the second-ever spacecraft to enter interstellar space. This occurred 119 astronomical units from the Sun. 1 astronomical unit is the distance between the Sun and the Earth, which is 93 million miles or 150 million kilometers. Voyager 1 had done this years earlier, and that was because it had fewer detours than Voyager 2. The former stopped over at Uranus and Neptune to conduct flybys. However, Voyager 2 was the first spacecraft to directly sample the electrically charged hazes or plasmas filling interstellar space and the solar system's farthest outskirts. Voyager 2 was able to analyze solar winds, the composition and behavior of plasma particles, the interaction of cosmic rays, the structure and direction of magnetic fields, and other traits that define the edges of the solar system. Even today, scientists are still publishing papers based on the data Voyager 2 returned as it was escaping from the solar system. The crossing into interstellar space by Voyager 2 has helped us learn a lot about the boundary of the solar system. While showing us entirely new things, the event has also challenged some ideas we had about the boundary before. However, to get the correct perspective of Voyager 2's latest findings, it's important to know how the Sun works. Contrary to what you might have thought, the Sun isn't a quietly burning ball providing illumination. Instead, it's a raging nuclear furnace speeding through the galaxy at about 450,000 miles an hour as it orbits the galactic center. Of course, you may not feel the high speed because of the massive size of the solar system, but apart from the speed and enormous heat, the Sun is a constant source of magnetic fields, causing its surface to constantly throw off a breeze of electrically charged particles called the solar wind. This gust spreads out in all directions, carrying the Sun's magnetic field with it. Eventually, the solar wind runs into the interstellar medium, the debris from ancient stellar explosions that lurks in the spaces between stars. Like oil and water, the solar wind and the interstellar medium don't perfectly mix. This makes the solar wind create a bubble within the interstellar medium known as the heliosphere. According to records from the 2 Voyagers, this bubble stretches about 11 billion miles from the Sun at its leading edge. It envelops the Sun, all 8 planets, and much of the outer objects orbiting our star. Note, though, that the heliosphere acts as a shield. It protects everything within it from most of the galaxy's highest energy radiation. Without it, your DNA would have been tampered with. However, the heliosphere has an outer edge known as the heliopause, which is where interstellar space starts from. Now, what does this boundary look like? Knowing this can assist us in picturing our sun's journey through the galaxy. It will also tell us more about the situations of other stars scattered across the cosmos. For these reasons, scientists were excited as Voyager 2 neared the boundary. Bear in mind that some instruments on Voyager 1 stopped working before it crossed the boundary, so there was no way to track its journey during that transition period. However, with the crossing of Voyager 2, researchers could see what happens to an object as it comes within 140 million miles of the heliopause for the first time. They discovered that the plasma surrounding the spacecraft slowed, heated up, and got denser. But once it got to the other side of the boundary, the interstellar medium got far hotter, about 54,000 degrees Fahrenheit. This was hotter than scientists had imagined. If you wonder how Voyager 2 managed to survive the heat, the plasma was very thin and diffuse, making the average temperature around the Voyager probes remain extremely cold. Voyager 2 also confirmed a theory that the heliopause is kind of a leaky border. These leaks actually go both ways. Before Voyager 1 passed through the heliopause, it zoomed through tendrils of interstellar particles that had punched into the heliopause like tree roots through rock. However, when it came to Voyager 2, the spacecraft encountered a trickle of low-energy particles that extended more than 100 million miles beyond the heliopause. Another mystery appeared as Voyager 1 came within 800 million miles of the heliopause, where it entered a limbo-like area in which the outbound solar wind slowed to a crawl. Before it crossed the heliopause, Voyager 2 saw the solar wind form an altogether different kind of layer that was nearly the same width as the stagnant one seen by Voyager 1. Voyager has also proven that the Sun's influence extends outside the solar system. The Sun is always spitting out shock waves of plasma known as coronal mass ejections or CMEs. They actually participate in shaping the rest of the solar system. However, Voyager 2 data showed the way CMEs propagate beyond the heliopause and create the effect of lowering the amount of cosmic rays beyond the bubble. This is somewhat similar to what you might find out in the galaxy. Supernovae send shock waves out into the galaxy as well, stirring the interstellar medium, although not as strongly as CMEs. Even the solar system's formation was triggered by an interstellar shock wave from a supernova. If we think about the potential for cosmic rays to promote biological mutations in life on Earth, Voyager 2 suggests that the Sun could also have an influence on the possible evolution of living things on extraterrestrial worlds in this planetary system and elsewhere. Solving the puzzles of interstellar space demands a better view of the heliosphere. Voyager 1 exited near the heliosphere's leading edge where it collides with the interstellar medium, and Voyager 2 exited along its left flank. Since there is no data on the heliosphere's wake, we are yet to figure out the overall shape. For all we know, the interstellar medium's pressure might maintain the heliosphere roughly spherical, or it could have a tail like a comet, or it's shaped like a croissant. The Voyagers are not the only spacecraft moving about in space. The problem, however, is that while they will eventually get to the heliospheres, they are also headed out of the solar system. They will never be able to return data. Well, NASA equipped each of the Voyagers with 3 radioisotope thermoelectric generators, RTGs, mounted at the end of a boom. These are one of the simplest possible forms of nuclear power. A brick of radioactive material surrounded by layers of thermocouples which use the temperature contrast between the hot radioactive brick and cold space to produce electrical power. The RTG units on Voyager 1 and 2 use plutonium-238. This isotope of plutonium undergoes decays only by producing alpha particles, which are absorbed within the RTG itself and so don't irradiate the other electronics in the spacecraft. As the plutonium decays with time, the amount of power it produces drops and the brick slowly cools. And as the brick cools, the efficiency of the thermoelectric generator also drops. Plutonium-238 has a half-life of 87.7 years, so the spacecraft's power supply would decrease by 0.787% per year. However, the actual electrical power available has dropped somewhat faster than that, due to the efficiency of the thermocouples decreasing and progressive degradation of various electrical components in the spacecraft. In fact, at the end of 2000, after 23 years in flight, the spacecraft's power supplies were only producing about 67% of what they were at launch. The first images of Jupiter from Voyager 2 began arriving on April 24, 1979, blessing us with time-lapse movies of atmospheric circulation. Unlike Voyager 1, Voyager 2 made close passes to the Jovian moons on its way into the system, with scientists especially interested in more information from Europa and Io. This close encounter yielded spectacular photos of the Jovian system as a whole, including its moons Callisto, Ganymede, Europa, Io, and Amalthea. Voyager had surveyed these moons before, but Voyager 2 managed to get closer. In fact, Voyager 2 got about 127,830 miles, or 205,720 kilometers close to Europa. Voyager 2's shortest distance from Jupiter was at a range of about 400,785 miles, or 645,000 kilometers. It transmitted new data on the planet's clouds, its newly discovered 4 moons, and ring system, as well as 17,000 new pictures. Remember the Pioneer spacecraft? They too had flown by Jupiter, and they detected few atmospheric changes from one encounter to the second. But Voyager 2 detected many significant changes, including a drift in the Great Red Spot, as well as changes in its shape and color. Thanks to the combined cameras of the two Voyagers, we've been able to map at least 80% of the surfaces of Ganymede and Callisto to a resolution of about 3 miles or 5 kilometers. 2 hours after its closest encounter with Jupiter, Voyager 2 had a course correction and sped off in the direction of Saturn. The new trajectory was decided by a decision made in January 1981 to send the spacecraft to Uranus and Neptune later in the decade. In August of 1981, Voyager 2 had its encounter with the 6th planet, 2 years after leaving the Jovian system. It started with the imaging of the moon Iapetus. Once again, Voyager 2 repeated the photographic mission of its predecessor, although it came about 14,290 miles or 23,000 kilometers closer to Saturn. The closest encounter to this planet was in August 1981 at a range of about 63,000 miles or 101,000 kilometers. The spacecraft provided more detailed images of the ring spokes and kinks and the F-ring and its shepherding moons, all found earlier by Voyager 1. Voyager 2's data suggested that Saturn's A-ring was perhaps only about 980 feet or 300 meters thick. As it flew behind and up past Saturn, the probe passed through the plane of Saturn's rings at a speed of 8 miles per second or 13 kilometers per second. During this period, the spunky spacecraft was hit by thousands of micron-sized dust grains that created puff plasma as they were vaporized.
After the Saturn flyby, the Voyager 2 scan platform got stuck, and it just wouldn't move. And so we just saw outbound these pictures of Saturn, and we wondered, could we fix it?
As a result, the particles repeatedly shifted the spacecraft's attitude, and its attitude control jets automatically fired many times to stabilize it. Despite the scare of the encounter, Voyager 2 managed to photograph the Saturn moons Enceladus, Tethys, Phoebe, Helene, Telesto, and Calypso. By now, Voyager 2 had fulfilled its primary mission, but the mission planners were not going to allow the spacecraft to retire. Instead, they directed the accomplished spacecraft to Uranus, a journey that would take about 4.5 years. In fact, its encounter with Jupiter was optimized in part to ensure that future planetary flybys would be possible. Even the Uranus encounter's geometry was meant to enable a future encounter with Neptune. However, at this stage, Voyager 2 began to record its own firsts. For example, Voyager 2 was the first human-made object to fly past the planet Uranus. Also, at this point, signals from the space vehicle were taking about 2.5 hours to reach the Earth. This was a signal traveling at the speed of light, and here light conditions were 400 times less than terrestrial conditions. Voyager 2 had its closest approach to Uranus in January 1986 at a range of about 50,640 miles or 81,500 kilometers. During its flyby, it discovered 10 new moons. They were given names like Puck, Portia, Juliet, Cressida, Rosalind, Belinda, Desdemona, Cordelia, Ophelia, and Bianca, obviously inspired by Shakespeare. Voyager 2 also discovered 2 new rings in addition to the older 9 rings and something rather novel, a magnetic field tilted at 55 degrees off-axis and off-center. The spacecraft found strong winds on Uranus, moving at up to 415 miles per hour or 724 kilometers per hour, and also evidence of a boiling ocean of water some 497 miles, 800 kilometers below the top cloud surface. Voyager 2 also captured spectacular photos of Miranda, Oberon, Ariel, Umbriel, and Titania, all moons of Uranus. After the Uranus encounter, the spacecraft set off for Neptune, making it about 4.3 billion miles or 7 billion kilometers away from the Earth. Voyager 2 flew about 2,918 miles or 4,800 kilometers over the cloud tops of the giant planet, the first human-made object to fly by the planet. It discovered 6 new moons: Proteus, Larissa, Despina, Galatea, Thalassa, and Naiad, in addition to 4 new rings. Voyager photographed 2/3 of Neptune's largest moon, Triton, revealing the coldest known planetary body in the solar system and a nitrogen ice volcano on its surface. The flyby of Neptune concluded Voyager 2's planetary encounters, which spanned an amazing 12 years in deep space, virtually accomplishing the originally planned grand tour of the solar system in terms of targets reached. Once past the Neptune system, Voyager 2 followed a course below the ecliptic plane and out of the solar system. Approximately 35 million miles or 56 million kilometers past the encounter, Voyager 2's instruments were put in low power mode to conserve energy. After the Neptune encounter, NASA formally renamed the entire project the Voyager Interstellar Mission (VIM). Of the 4 spacecraft sent out beyond the environs of the solar system in the 1970s, 3 of them, Voyagers 1 and 2 and Pioneer 11, were all heading in the direction of the solar apex. This means they were going in the apparent path of the Sun's travel in the Milky Way galaxy, and thus would be expected to reach the heliopause earlier than Pioneer 10, which was headed in the direction of the heliospheric tail. To conserve more energy, NASA permanently turned off non-essential instruments in November 1998, leaving 7 instruments still operating. This was 21 years after launch. Through the turn of the century, NASA's Jet Propulsion Laboratory, JPL, continued to receive ultraviolet and particle fields data. For example, in January 2001, an immense shockwave that had blasted out of the outer heliosphere in July 2000 finally reached Voyager 2. During its 6-month journey, the shockwave had plowed through the solar wind, sweeping up and accelerating charged particles. Voyager 2 sent back valuable information on the high-energy shock-energized ion. In August 2007, Voyager 2 passed the termination shock and then entered the heliosheath. By November 2017, the spacecraft was 116.167 AU, which is about 10.8 billion miles or about 17.378 billion kilometers from Earth, moving at a velocity of 9.6 miles per second or 15.4 kilometers per second relative to the Sun. It was headed in the direction of the constellation Telescopium. On November 5, 2018, Voyager 2 crossed the heliopause. This is the boundary where solar wind influence ends. From that point on, Voyager 2 was in what is known as interstellar medium, or space. Voyager 1 had crossed it years before, although there were controversies. But at this point, Voyager 2's plasma instrument detected the leap in particle density as protons, electrons, and other charged particles struck the instrument. It also recorded the temperature between 30,000 and 50,000 Kelvin. On July 8, 2019, Voyager 2 successfully fired up its trajectory correction maneuver thrusters and will be using them to control the spacecraft's pointing for the foreseeable future. Voyager 2 last used those thrusters during its encounter with Neptune in 1989. The spacecraft's aging attitude control thrusters have been experiencing degradation that required them to fire an increasing and untenable number of pulses to keep its antenna pointed at Earth. Voyager 1 had switched to its trajectory correction maneuver thrusters for the same reason in January 2018. To ensure that both vintage robots continue to return the best scientific data possible from the frontiers of space, mission engineers had to implement a new plan to manage them. The plan required making difficult choices, particularly about instruments to keep running and thrusters. The spacecraft is billions of miles away with signals taking more than 17 hours to reach us. However, Voyager 2 continues to go strong. Let's hear what you think of the enduring Voyager mission in the comment section.